Welcome to Module 4, Development Concept Selection and Reservoir Management. In the previous modules, we defined the reservoir, developed production forecasts, and built the wells plan. Now we reach one of the most important stages in the entire FDP process, deciding how the field will actually be developed. This module examines how subsurface information, wells planning, facilities design, and commercial considerations come together to select the development concept and manage the reservoir throughout its producing life. Concept selection is where planning becomes reality. At this stage, the subsurface model and wells plan are translated into physical infrastructure, facilities, export routes, and field layouts. This is often considered the highest value decision in the FDP because it commits most of the project's capital and is extremely difficult to reverse after sanction. The best teams avoid becoming attached to the first workable option. Instead, they generate multiple concepts, screen them systematically, and progressively narrow the alternatives. Remember the stage gate framework from Module 1. Concept selection is the central objective of the select phase and one of the most critical decision points in the entire project lifecycle. When comparing development concepts, 4 broad criteria are normally evaluated. The first is technical feasibility. Can the concept safely and reliably produce the reservoir over its expected life? The second is cost and schedule. What is the capital investment, operating cost, and time required to reach production? The third is HSE and environmental performance. Different concepts carry different safety risks and environmental impacts. The fourth is commercial fit. This includes fiscal terms, infrastructure access, market opportunities, and partner expectations. A common mistake is to optimize for only one criterion. The lowest cost option may not be the safest. The safest option may not be the most economic. The goal is to identify the concept that provides the best overall balance across all 4 areas. Onshore development concepts are generally simpler than offshore concepts. Production from individual wells is gathered through flowlines and transported to a central processing facility, or CPF. The CPF separates the oil, gas, and water streams before preparing them for export or disposal. Export is typically through pipelines, although trucking or rail may be used for smaller developments. One of the biggest advantages of onshore development is modularity. Additional processing capacity can often be added as production grows, allowing operators to expand facilities progressively rather than committing all capacity upfront. This flexibility is one reason onshore projects are often considered more forgiving than offshore developments. This slide introduces the major offshore development concepts used around the world. Fixed platforms are attached directly to the seabed and are most common in shallow water. Floating platforms, such as TLPs and spars, extend development into deeper water while still supporting surface wells. FPSOs, or floating production storage and offloading vessels, process and store hydrocarbons onboard before transferring them to tankers. Subsea tiebacks connect seabed wells to existing host facilities, avoiding the cost of building a new platform. Floating LNG, or FLNG, allows gas to be liquefied offshore without requiring a pipeline to shore. Semi-submersibles provide another floating solution across a wide range of water depths. By the end of this module, you should be able to look at a field's water depth, reservoir size, and location and identify which concept family is likely to be most suitable. Concept selection is influenced by both technical and commercial considerations. On the technical side, water depth is often the first screening factor because it determines which concepts are physically feasible. Distance to shore and existing infrastructure influences whether pipelines, floating storage, or tiebacks are more attractive. Reservoir size and expected production rates help determine the required processing capacity. Environmental conditions such as waves, currents, and cyclones also influence the design. Once feasible concepts have been identified, commercial factors become increasingly important. Existing infrastructure, development phasing, market access, fiscal terms, and local content requirements may ultimately determine which option is selected. A useful way to think about concept selection is that engineering defines what is possible, while commercial evaluation determines what is preferable. This slide summarizes many of the relationships we've discussed. The first figure shows how different development concepts become more or less suitable as water depth changes. The second figure highlights the multidisciplinary nature of reservoir management, bringing together subsurface, wells, facilities, and operational activities. The third figure illustrates a subsea tieback arrangement, where seabed wells are connected to an existing host facility. Taken together, these graphics show that concept selection is ultimately about matching field characteristics to the most appropriate development solution. Shallow water developments in regions such as the Gulf of Mexico Shelf and Southeast Asia have traditionally relied on fixed platforms. These structures are mature, well understood, and cost-effective in relatively shallow water. As these basins mature, another pattern emerges. Large networks of existing platforms and pipelines create opportunities for smaller future discoveries to be tied back to existing infrastructure. Over time, mature basins often evolve from standalone developments toward infrastructure-led developments. This links directly back to the Southeast Asia case study from Module 3, where facilities and wells were optimized together across multiple smaller fields. In deepwater regions such as offshore Brazil, West Africa, and parts of the Gulf of Mexico, FPSOs have become the dominant development concept. A major advantage of the FPSO is that it removes the need for long export pipelines by storing oil onboard and offloading directly to tankers. FPSOs also provide flexibility because some vessels can be redeployed to other developments later in their life. Another advantage is the flexibility of subsea well placement. Wells can be positioned optimally across the reservoir and connected back to a central FPSO through subsea infrastructure. This case highlights an important lesson. The same concept that is highly attractive in deepwater may be completely unnecessary in shallow water developments. The North Sea provides one of the best examples of infrastructure-led development. Many newer discoveries are too small to justify standalone facilities. Instead, subsea wells are connected to nearby host platforms that already possess processing and export infrastructure. This significantly reduces capital expenditure and shortens development schedules. However, tiebacks also create a dependency. Their economics depend on the remaining operating life of the host facility. If the host platform approaches decommissioning too soon, the value of the tieback can be severely reduced. This demonstrates how development decisions today can influence opportunities decades into the future. Once production begins, planning does not stop. A Reservoir Management Plan, or RMP, provides the framework for developing, monitoring, and optimizing the reservoir throughout its life. The RMP integrates reservoir engineering, geoscience, production engineering, drilling, facilities, and economics into a single coordinated plan. Unlike the FDP, which supports a major investment decision, the RMP is continuously updated as new information becomes available. The most effective RMPs also define specific triggers for action. For example, if pressure declines faster than expected or production falls below forecast, predefined actions can be initiated. In many ways, the RMP is where the planning work from Modules 2 and 3 becomes a living operational process. Effective reservoir management depends on continuous surveillance. One important tool is 4D seismic, which tracks fluid movement and pressure changes throughout the field over time. Another tool is production logging, which identifies which reservoir intervals are actually contributing production. Pressure surveys help confirm whether depletion, aquifer support, or injection performance are behaving as expected. The purpose of monitoring is not simply to collect data. The purpose is to compare actual performance against forecast performance. When significant deviations appear, the reservoir model can be updated and development plans adjusted accordingly. One lesson that repeatedly appears throughout FDP is that uncertainty never completely disappears. For this reason, many developments intentionally incorporate flexibility. Examples include spare platform slots, expandable subsea systems, and modular processing capacity. Another common approach is phased development. Instead of fully developing the field immediately, operators sanction an initial phase and expand later as uncertainty reduces. This can be particularly valuable when the gap between P90 and P10 outcomes is large. The trade-off is that flexibility costs money. The challenge is determining how much optionality is worth paying for today in order to reduce future risk. Let's summarize the key messages from this module. Concept selection is often the highest value decision within the field development plan. Water depth and infrastructure access are the primary technical drivers of offshore concept selection. Existing infrastructure frequently makes tieback developments more attractive than standalone facilities. Reservoir management is an ongoing process that integrates subsurface, wells, facilities, and operational performance. Finally, flexibility and phased development create resilience against uncertainty, although that flexibility comes with an associated cost. So far, we have defined the reservoir, developed the wells plan, and selected the development concept. The next question is whether the project creates sufficient value to justify investment. In Module 5, we examine project economics, final investment decision, execution planning, and the full life of field journey through to decommissioning. This is where technical planning becomes business decision-making.